This is the lecture for section 5E on correlation and causation. Anytime we're working with that paired data where we're trying to see if there is a relationship between two pieces of information, we can talk about correlation and causation. A correlation exists between two variables when higher values of one consistently go with higher values of another, or if higher values of one mean lower values of the other variable. Correlation just means that there's some sort of either positive relationship or a positive negative relationship between them. Causality or causation can only be proven through an experiment. So correlation is usually just observed kind of data and patterns. Causation has to be done with an experiment. And this means that one factor is the direct cause of the other factor. Let's look at some examples of correlation. There's a correlation between the two variables, height and weight. Generally speaking, the taller you are, the more you weigh, but that is not always the case. It's just a general trend that we see in nature. So there is some sort of positive correlation or relationship between those two variables. There's another relationship between the demand of apples and the price of apples. If the price of apples is low, more people will probably buy them than if the prices are high. Does that mean that one is the direct cause of the other? Not necessarily. There is also a correlation between practice time and skill among piano players. That is, generally speaking, the more you practice, the better you become. However, there are exceptions to those rules, all right? There are some that are just naturals. And so we can't just say this causes the other. We're just talking in general, there is a relationship between certain variables. So the biggest thing to note here is that correlation does not imply causation. Just because there is a relationship does not mean that one causes the other to occur. Here's an example. When crime increases, sales of ice cream tend to increase. Okay, this is just a general fact that we have come to find. Does that mean that crime increases causes ice cream sales to increase? No. That's not possible. We can't say that one causes the other. It's actually just something that happens when there's warmer weather. When there's warmer weather, we have more ice cream sales. When there's warmer weather, there is more crime. So just because two things relate to each other or there is a relationship does not mean that one specifically causes the other to occur.
There is a graph that we can use to represent two variable data. And that is a scatter plot. So we talked a little bit in the last section about how we can make graphs in StatCrunch, and we're going to make another graph in StatCrunch today called a scatter plot. So we will work through the whole process here again of getting into StatCrunch. Our class, Pearson MyLab, home. Give it a second. And then StatCrunch. And I'm going to open. What I'm going to do is I'm going to enter my first variable here, which is miles. So 2, 12, 3, 27, 15, 8, 4, and 18. And the second variable is minutes. So we're tracking our commute distance and our commute time it takes to get. So basically how far I am away from my job, as well as how long it takes to get there. And And I bet that you guys can already take a guess as to what may happen or what you may see here. We're going to make a scatter plot to get started. So we're going to go to graph, scatter plot. Your first column is always your X column. Your second column will always be your Y column. And then I'm just going to click compute, and we are going to get a graph here. All right, so this is a scatter plot. It is going to have a pair of points represented by a dot, and I can click on that one. It'll show me exactly which one it is, 310. I can click on that one, that's 221. Or I can kind of hover over them and it does show me where they're located.
Now, there are different types of relationships that can happen. The one we just saw is going to be this one here, a positive correlation. What happens is the graph or all the points tend to go up from left to right. As I increase the one, the other one increases, which makes general sense here. If I live farther away from work, it's going to take me longer to get there. We do have the option of having no correlation whatsoever. If the points don't seem to follow any sort of linear pattern, we're going to say there's no relationship. We can also have a negative correlation. So it's going to look like this. The slope of the line is going to be going down from left to right. And as we increase one, the other one decreases. After we determine what type of correlation we have, we can then talk about the strength of it. However close the points are to a general trend line that we can kind of draw in there, the stronger the relationship's going to be. So if my points are very close to what I would draw a line here, I would have a very, very strong relationship. If, however, so this is strong, if, however, your points are generally going up, but they're all kind of all over the place. If I try to, graph a line to kind of show the trend there, it's weaker because there's a lot more spread between the points and the line. These points are not as close to the line, so this wouldn't be as strong of a relationship as this one here. So anytime we talk about our correlation, we will say two things: if it is positive or negative, and the strength. This is a graph of a positive correlation. This scatter diagram is for the weight in carats of a diamond and the price that it costs in dollar. Generally, the more carats it is, the more it costs, but there are other variables to deal with. The cut of the diamond, the color of the diamond, the clarity of the diamond. So the price of the diamond is not solely dependent upon the weight. There are other pieces that make that value up. So we can't say that just this one causes the other. It is just a relationship. There are other variables involved in making the price change. This is a negative correlation graph. And you can see generally like this, it goes down. And we are comparing here life expectancy and infant mortality. So that would make sense. The lower my infant mortality rate, the longer I would expect to be able to live. If your infants cannot live very long, then your general population is not going to live very long. So again, a correlation, a relationship, there are clearly other things that play into this. It's not just these two variables that cause one of the other to occur. It's just a relationship. These two scatter plots here show 2 weeks of data comparing the actual high temperature for the day with the same day forecast. So that's on the left. So the actual temperature compared with what they forecasted. And then on the right here, this is the 3-day forecast. So 3 days ahead what they predicted and what the actual was. What types of correlation do we have here? Both scatter plots show a general trend in which a higher predicted temperature means a higher actual temperature. That is, that both show positive correlations. The points in the left diagram, though, are closer to what we predicted. It's easier to predict the temperature for the day you are predicting. The ones you're predicting 3 days in advance have more variability. There is a larger chance you are wrong, and therefore those points are a little further spread apart, so they would not be as strong of a correlation. Some possible explanations for there to be a correlation between variables. In some cases, it may just be coincidence. In other cases, the variables might be directly influenced by some common underlying cause or some other variable that both impacts them. So, for example, that crime and ice cream sales. Well, what impacted both of them? The temperature outside. Could we clearly say that temperature is the cause of this? Maybe not, but there is a common variable that impacted both of those variables. Third one is, in fact, that one is the actual cause of the other. Now, even if this is the case, it may be only one of several causes. It may not be the only cause that makes this happen. So let's go back and consider that negative relationship we had between infant mortality and life expectancy. That was the graph back on slide 9. Which of the three do we think is accurate? Is it just coincidence? Is there some common variable, or is one in fact the cause of the other? Well, it is negative because of some common underlying cause or some common underlying issue, which is healthcare or your quality of life, your quality of water, that all that stuff generally put under your quality of health. In countries where you do not have good water, good healthcare, things like that, you do not have a higher life expectancy. You tend to die out faster versus countries that have very good healthcare, very good water, food sources, things like that. If, however, you suspect that something is truly the cause, here's some guidelines that we have to follow. You want to look for situations in which the effect is correlated with our suspected cause, even while other factors vary. You want to check among groups that differ only in the presence or absence of the suspected cause, that the effect is similarly present or absent. You want to look for evidence that larger amounts of the suspected cause produces larger amounts of the effect. If the effect may be produced by other potential causes, we need to make sure that the effect still remains after accounting for those. We've got a few more on the next slide. If it's possible, you're going to test the suspected cause with an experiment, because the only way you can truly prove causation or causality is with an experiment. Now, the thing is, though, there are certain experiments that cannot be performed with humans due to ethical reasons, or animals and things like that. You cannot give an infant certain drugs to see how that impacts them. We cannot put people in a car and tell them, you must wear a seatbelt, you can't, and then crash them together. That is not ethical. So there are certain things that we will never be able to truly test with an experiment. So one other option is to try to determine the physical mechanism by which the suspected cause produces the effect. There was a case study done for airbags and children. By the mid 1990s, passenger side airbags had become commonplace in cars. Statistical studies showed that the airbags saved many lives in moderate to high speed collisions. But a disturbing pattern also appeared. In at least some cases, young children, especially infants or toddlers in child car seats, were killed by these airbags in low speed collisions. At first, a lot of the safety advocates found it difficult to believe that these airbags could actually be the cause of the death when they were saving other people's lives. But there was a lot of evidence that was gathered to show that. Now, remember, these are observational, case studies are observational, and that observational evidence met those first four guidelines we talked about to establish causality. So the greater risk to infants in car seats fit guideline 3 because it indicated that being closer to the airbags increased the risk of death. A child car seat sits on top of the built-in seat, thereby putting a child closer to the airbag than the child would have been otherwise. So that's something to look at. Because they could not do this test on actual humans, they did their next best type of experiment using dummies. And they've used those dummies and found that because of the children's size and where they were sitting, they could have been easily hurt by the explosive opening of the airbag. So basically, what it showed us is those experiments show that the airbag could impact a child car seat hard enough to cause death, thereby revealing the physical mechanism by which death occurred would have been the airbag. So they actually were able to show here that there is a cause and effect here, and we need to be careful with where we place these airbags in the cars, especially around children in car seats. We can have different levels of confidence in our causality. One could be, we think it's just a possible cause. We've determined there is a relationship, but we really can't determine yet. We haven't gathered enough information to say, does this relationship actually lead to a causal relationship? So, for example, in the legal system, possible cause, such as thinking that a particular suspect might be the cause in a particular crime, you can start the investigation. It does not mean that that person is, in fact, your only suspect, and you must only go with them. We also have a probable cause. We have good reason to suspect the correlation does, in fact, involve a cause. Perhaps some of those guidelines, those 6 guidelines that we talked about, have already been satisfied. And looking at the legal system, probable cause is the general standard that you need in order to get a judge to warrant for example, a wiretap. Basically meaning you've gathered more evidence than you had before to show more of a causal type relationship. The final option is cause beyond a reasonable doubt. Meaning, we have found a physical model based on our experiment to explain how one officially causes the other without any doubt. In the legal system, cause beyond reasonable doubt is the usual standard for conviction. After you have gone through the entire court process, you have to have reasonable doubt. You cannot have reasonable doubt, but it does not mean it's all doubt has been eliminated. There is always a small chance you got it wrong. We know that in the legal system, we have found that people have been falsely convicted, even though the jury believed beyond a reasonable doubt that they were, in fact, the person who committed the crime. So there is always a chance that we did find something wrong, but we've gathered so much evidence that we would say we have beyond a reasonable doubt. Below is the scatter plot, and it's talking about the average years of education and the gross domestic product per person. And we have different colored circles. We also have different sized circles, and they all represent different things. The graph clearly says that it shows data from over 100 countries on the average number of years of education of its population above age 15 and the size of its economy as measured by the gross domestic product or GDP per person. The size of the dots represents the country's population. So a larger dot represents a larger population. What I would like you to do here is use this slide to be your comment slide. Pick one of the four questions, A, B, C, or D, and reply with your answer. So you can tell me A, what type of correlation do you have? Positive or negative, weak or strong? B, can you write a sentence that interprets the relationship between these two variables? C, what level of confidence would you have that there's a causal relationship between education and economic strength? Or D, the varying sizes of the dots are a new feature not seen in our other scatter plots. So briefly comment on what that additional information helps you learn from here.
Last example here, we are going to look at the average income for some states as well as the percentage of the population below poverty level. I've already gone and entered the data into StatCrunch, so you don't have to watch me type all of that in. But we are going to run a scatter plot. I'm also going to show you a different way we can make a scatter plot that may give us just a little bit of extra information. So the other way we can do this is you can go to Stat, you're going to click on Regression and Simple Linear. X is the income, the first column here, and Y is the percent. I'm going to click Compute. And I know right now you're going to get this whole big box of information and you're going to say, Professor Ryba, I don't know what any of this means, and that's okay. Right now, we're just going to arrow over to the second slide. So the second slide here is the graph, but you also have what's called your fitted line or your trend line. So you should be able to see here, because it says after you make your scatter plot, decide what type of correlation you have. Well, if I look at my line here, it's going down from left to right. So I have a negative relationship. What we're seeing here is as I increase my average income, the percentage of my population below poverty level goes down. In part B, they said you could optionally talk about this correlation coefficient and then the squared of the correlation coefficient. Most times in statistics, we actually look at this variable here, the R correlation coefficient. That's usually the one that gets looked at more because this tells me right here that negative in front of it means I have a negative relationship. And then how close this number is to 1 tells me how strong it is. So given that it's in like the 0.6s, I would say it's a moderate negative. If it's strong, you're going to see like 0.9s, 0.8s. The closer you get to 0.5, the more moderate and weak. So if you're getting towards like 0.4 or 0.3, you've got a pretty weak relationship. So usually I like to look at this one. They do talk about the R squared here. We're not going to talk about that, but I did want to show you the correlation coefficient. Other things it shows you here, hey, your slope is negative. That goes right along with your negative relationship here. Okay, so does it make sense? Does it make sense that if people are earning more money on average, that we would have less people below poverty? Yes, that makes logical sense. Would I say that it's beyond a reasonable doubt the only cause? No, there could very easily be other things that are impacting that as well. All right, that is the end of this section.